All right, today we have a talk from Laura Iacconi, who recently joined us here at Queen Mary as a postdoc, who previously did a PhD at the University of Portsmouth, and today we'll be talking about small-scale fluctuations in exponential alpha-attractor inflation. Okay, so take it away.
Okay, cool. So, before starting, I would like to this talk to be useful. So I put some introductory material at the beginning of it, especially for people that are not particularly familiar with cosmological inflation. And I love to be interrupted, and please do if I say something that doesn't make sense or you want some clarification while the talk is happening. You don't need to wait to the end. So today, I would like to talk about the last paper that I did during my PhD with David, Bouchard, and Matteo in Portsmouth. And I've decided to talk about this because this is the starting point of the work that we are currently doing here with David. So in light of future discussions about what's going on with what we're doing here, I think it's good to have this introduction. So let's see if the slides work. Yes. So I will start with an overview of cosmological inflation and how to test the inflation of small scales. And then I will focus on the main topic of our work, which is looking at these small scale fluctuations in cosmological alpha-attractors. And I will discuss in particular the impact that large scale observation have on the small scale phenomenology. So let's start from here. So this is a cartoon that represents what is the exponential expansion history of our universe. And in cosmological inflation, which is a period of accelerated expansion in the very early universe, sits here at the very beginning. So it was initially introduced as a theory in the 80s in order to reconcile some problems, some issues within the hot Big Bang cosmology. And it later sticked around and became the leading paradigm for understanding how was the very early universe, what happened there. And I will mention some of the successes of cosmological inflation in the next minutes. So let's start from how do we implement inflation within the simplest models. Okay, so these are single field slow roll inflationary models, and inflation is defined as an accelerated expansion, and you can work this out to understand that this comes together with a Hubble rate, which is defined here, that it should be constant during inflation. Now, if you go and look how the scale factor changes with time during inflation, you will find that it grows exponentially, and the amount by which it grows depends on the Hubble rate during inflation. Now, you can describe things using cosmic time as time variable, but usually in inflation, we use another time variable, which is the number of e-folds. So the number of e-folds n is defined as the integral of the Hubble rate. And you just remember it because basically it's telling you how many e-folds has the scale factor grown during inflation. So if we try to realize this, so an almost constant Hubble rate with a simple single field model, we will start by looking at these at this action. So we have a scalar field endowed with some potential that is minimally coupled to gravity. Now, let's entertain the possibility that the inflaton potential is almost flat. Well, a consequence of this is that pi will be moving very slowly. And if pi moves slowly, means that when we go and look at the contribution to the Hubble rate during inflation, which they will be coming from the potential of the inflaton and its kinetic energy, for an almost flat potential and a slowly rolling field, this term can be neglected. And the Hubble rate is almost given in terms, is just basically given in terms of the potential. And if this is flat enough, this will be constant. Okay, so this is the mechanism for realizing single field slow-roll inflation. Now, more to say, formally, you can find a hierarchical, I always do that, series of slow-roll parameters. And in order to have successful inflation, these have to be smaller. So here I list just the first two of these, epsilon h and eta h. So epsilon h is telling you how much h is changing with time. We know that it has to be almost constant. So inflation happens with epsilon h is small, and the same and eta h as well, and all the series. So pictorially, we can put, say, on this picture what I've just said in words and equations. So we have our inflaton, who is traveling, evolving on a particularly flat region of its potential. And during this evolution, which happens in slow roll, when slow roll is valid, this is when inflation happens. So let's say that the observable inflation happens between when the inflaton moves from phi initial to phi end. When the inflaton gets out of this flat region, it will start moving faster. So what happens is that we can no longer ignore its kinetic energy. Epsilon will be no longer small, it will get to 1, and that's when formally we say that inflation is ended. Now, okay, so now you are in this situation in which you have realized cosmological inflation, your expansion, and the universe is filled with this scalar field. So we need to explain how the scalar field and or its decay products then decay into standard model particles. And this is the process that is known as reheating. So what happens is basically that you can imagine that the inflaton continues evolving and then starts oscillating, it reaches the minimum of the potential and it starts oscillating around here. And in this phase of the evolution, the standard model particles are produced. And I just want to point out something. So if you can approximate the minimum as a quadratic minimum, then the equation of state parameter for reheating is 0, which means that basically reheating can be described as a matter-dominated phase.
Just one question. In the model you showed, the scalar field has no coupling to the standard model. So
No.
How can this happen?
Because we are looking at this different regimes. Definitely, when you are studying reheating, you are looking exactly at these sort of terms.
So the coupling suddenly appears to.
Let's say that there are scales that regulate the Hubble, the Hubble scales that is telling you the energy scale during inflation, and then there is another parameter, another scale that tells you to say what is going on during the energy scale for reheating, and when inflation is happening, you really need to just care about.
Okay. Thank you.
So, okay, so now we have realized our exponential expansion, and it's the next step would be looking at perturbations during single field slow-roll inflation. So if we start from our unperturbed line element, together with the homogeneous field, which is the field that we have studied up to now, we can perturb the metric and the inflaton and then apply constraints and choose a gauge. And for example, in the moving gauge, we would end up with something like this. So this is the perturbed line element, and you see that two quantities have shown up with respect to the unperturbed one. And we have zeta, which is the scalar perturbation, and this tensor gamma ij, which is transverse and trace tensor, we basically describes tensor perturbations. So what we want to do now is understand what is the statistics of the perturbation that is produced within single field slow-roll inflation. So first we can look at the scalar power spectrum. So the power spectrum for the curvature perturbation, and within single field slow-roll inflation, this depends on the Hubble rate during inflation, the first slow-roll parameter, and this quantity has to be evaluated at horizon crossing. So for each mode, for each scale, when that crosses the horizon. Another thing that you want to do is to see how this quantity, the scalar power spectrum, depends on scale. So you can calculate the tilt, the spectral tilt. And you find in single-field solar inflation that this is given in terms of solar parameters. If you remember, these are small during inflation. So basically, this is telling you that within single-field solar inflation, we expect the power spectrum of scalar perturbation to be almost scale invariant because the tilt is very small. Moreover, single-field solar inflation predicts adiabatic perturbations and also the fact that non-Gaussianities are slower or suppressed. So they're expected to be small. You can then do the same and look at the tensor perturbations. So you can calculate the tensor power spectrum, but usually we do not discuss just the tensor power spectrum, but rather construct this quantity, which is the tensor to scalar ratio. So this is the ratio between the amplitude of tensor perturbation with respect to scalar perturbations. And in single-field solar inflation, this is given again in terms of the solar parameter epsilon h. So these are primordial gravitational waves that are sourced by vacuum fluctuations of the metric during inflation. And so this is to say that these are the predictions for the perturbations within single-field solar. So now you have your predictions from inflation, but in order to constrain inflation, we need to connect these predictions with late time observables. And I think that's doing that is quite useful to look at the scheme, like a scheme of scales like this one. So these are what I'm representing are comoving scales against time. And you see for time, I'm using this variable n. And, first inflation happens between NC and B, let's say observable inflation happens between NC and B and NN. And N signals the end of inflation. Then we have a reheating phase. And then we have the standard hot Big Bang evolution starting with radiation domination. In green, I'm representing the Hubble radius, which is shrinking during inflation and then it grows. And I am representing one scale in particular. So this is the CMB scale. Okay, so I'm just considering one specific scale. There will be many other scales here, but let's focus on this one. So the modes, the CMB modes, will start off in the subhorizon regime. This means that the wavelength of these modes is smaller than the Hubble radius, and then they are stretched by the exponential expansion to superhorizon regimes. So you see that here is the point at which they cross the horizon and they become larger. And then they stay on superhorizon until later times when they re-enter the horizon. And for example, they source the CMB, which then we detect here. Now, this picture is not on scale, so we don't live in radiation domination, but I hope that's clear. So very importantly, it was shown that on superhorizon scales within single-field solar inflation, the curvature perturbation is constant. So this is very crucial because it's telling me that whatever difficult stuff, difficult physics that maybe we don't completely have constraint and have control over, that happens here, this is constant, so I can connect directly what happens from here on to what was produced here. Okay, so this is a property that's very useful. So on this graph, I would like to highlight two quantities that are relevant when considering inflationary perturbations. These are the number of epochs that's elapsed between the horizon crossing of the CMB scale to the end of inflation. This is given in terms, this will depend on the inflaton potential and also depends on the duration of reheating. Now, the duration of reheating on this scheme is just the number of epochs that elapse between the end of inflation and the end of reheating. And we don't really know the temperature of reheating. And so therefore, how long reheating was. We have bounds on these quantities, but we cannot pinpoint exactly to specific values. So you see already that there is a an uncertainty that feeds into the determination of delta and CMB here. So, okay, so we understand how to connect single field predictions, which you calculate at horizon crossing during inflation, to late time observables. You understand what is the physics that produce the CMB, so you can just directly connect everything and look inside of the CMB for this primordial power spectrum. So if we model the scalar power spectrum as a power law with some amplitude and some tilt centered around this peak scale, KCMB, which I introduced before, then observations of the CMB tell us that the amplitude is of the order of 10 to the -9, and you see NS is almost, is not far from 1. It's not 1, but it's not far from 1. So this is telling us that the spectra of primordial fluctuations that we see in the CMB, these are almost scale invariant. If you remember, this is exactly how is predicted from single field inflation. And I want to also remind you that, I mean, you know this, but that is exactly then how all the structure formed, starting from these initial perturbations. Also, from observation of the CMB, we can go and look at non-Gaussianities, and these are at the moment consistent with 0. So these perturbations are highly Gaussian. Okay, and this again is predicted within a single field inflation. We can then look for primordial gravitational waves. So these have not been detected, but they are constrained. And if you look at the CMB polarization map, you can find that there is an upper bound on the tensor to scalar ratio. So let's, I think it's nice to give a look to the latest Planck results for comparing basically what you get from Planck observations combined with other data set, but what you get from CMB observations and BAO observations versus some interesting inflationary models. So we are looking at the marginalized 95% confidence level constraints in the tensor to scalar ratio versus street tilt plane. And there will be different contours, gray, red, and blue, depending on the data that you consider. Now, also you see that for each inflationary model, these predictions are not just points, but they are like extended. And this makes sense because this is just basically because who produced this plot is plotting predictions for this delta N CMB, they call it N star, but it's the same thing. Delta N CMB that ranges from 50 to 60. And this is just a way of keeping into account the fact that, remember, we don't know how long reading was, so we cannot pinpoint delta N CMB, that's the number, so therefore that's the prediction. We will have instead some predictions, a range. Okay. Next thing that
is there anything that prevents the upper bound on N star to be 1000?
Yeah, and the reasonable values of N star have to be between 40 and 70, sorry.
And where does that come from?
It comes from the bounds on the duration of inflation. But we can look at that. Yeah. Okay. For each inflationary model, by the way, you can calculate this quantity because you fix an inflaton potential, and then you need to understand what is the range of reading duration that is reasonable, and that will give you a range of delta N CMB. They just plot it between 50 and 60 because these are ballpark numbers that make sense for most inflation.
Is this connected to the horizon problem? Meaning that the size of the horizon would have been at least
The value of delta N CMB is connected with the inflation being a working solution for the horizon problem. Yeah. So another thing that we can see from this plot is that there are already some inflationary models that are disfavored, and these are single field monomial inflation. So stuff that lies here. You see that they are starting getting a bit far from the core of the contours. another thing that we can note from this plot is that there are these points corresponding to Starobinsky inflation or R-squared inflation, which really lie at the core of the contours. So this is a very compelling model for inflation. And then we can see another family of models that are the alpha-attractors, represented by this yellow band. And we will go a bit more in alpha-attractors later. So we have seen that on large scales, scalar power spectrum is very well constrained to be almost scale invariant. Perturbations have to be Gaussian to a very good level and stuff like that. But the question is, okay, so I know what happens here, but what happens here? What happens to small scales? So on small scales, I could have for example, two widely different situations. I can have a scalar power spectrum that continues to, slightly decrease, going towards small scales, or I can have a large enhancement. So it's not really sure, and we are not really sure, and it's important that we think about way of testing inflation on small scales. So let's consider a situation in which the scalar power spectrum grows and displays a peak. Then we can, in principle, test this in two ways, considering second order gravitational waves, so gravitational waves that are produced at second order in perturbation theory. When these large scalar perturbations, they re-enter the horizon, and they at second order in perturbation theory, they source gravitational waves. So this is not primordial gravitational waves. And then another thing that is very interesting can happen, which is that if the scalar power spectrum gets to values around 10 to the minus 2 or 5, 10 to the minus 3, then you can have primordial black hole production. So let's just give a look at these two things in more details. So if you have a large scalar power spectrum, a large peak in the scalar power spectrum, when these curvature perturbations re-enter the horizon and source density fluctuation, these can collapse to form primordial black holes. They are interesting to look at because they are candidate for dark matter and could explain some of the events of LIGO Virgo Cagliari events. As concerns second order gravitational waves, again, at horizon reentry, the curvature fluctuation sources density fluctuation, which at second order then source gravitational waves. So just to schematize this, the interaction that I have in mind is something like this. We will have a coupling between two scalar perturbations and the tensor mode. And so therefore, this sort of interaction will source the tensor power spectrum in this way. So schematically, second order gravitational waves are given by an integral of the square of the scalar power spectrum. And if p zeta is small, then the second order gravitational waves will be small. But if p zeta is large and exhibits a peak, then we might have the possibility to detect these gravitational waves and test therefore inflation. So just to conclude this first bit, inflation is at the same time, a great success, and it does still need some work. So inflation solves the hot Big Bang cosmology problems. It does see the large scale structure. It explains coherent phase of primordial fluctuation, which I didn't go into, but it's very important. And up to now, within the simple framework of single-phase floral inflation, we can explain observations. At the same time, there is some work that needs to be done yet. So there are strong motivations for which inflation was not a single field phenomenon. Let's say it was multi-field. So we need to understand really what fields drove inflation and possibly go beyond single field inflation. And another thing that I find interesting is really to try to understand what happens on small scales, because with CMB observation, we are really testing a specific region of the inflaton potential, and it would be nice to move away from there and understand what happens in the other 40 epochs of inflation. So this brings me to the topic of the work that I would like to discuss. And delve into this, let's start at giving a look with what are these cosmological alpha-attractors. So these are this is a compelling family of inflationary models. They are in accordance with the current CMB observations. So if you remember the plot from before, these are the contours. This is the yellow band corresponding to alpha-attractors, and you see that they are very well in accordance with CMB observations. They nicely lead to universal predictions for the CMB observables, and we will look into that. And they are interesting from a higher energy point of view because they can be embedded in supergravity theories and so on.
I have a question on this. Since you said they can be embedded in these high energy theories, does this mean that alpha-attractors don't rely on, say, symmetries, like they don't need it? Because, supersymmetry is often attacked for not having much evidence now as a thing, right? So
I think supersymmetry is like supersymmetry, isn't it one of the ingredients of supergravity?
yeah, so that's why I'm a bit confused about its embedding. So does it rely on this, or no? It doesn't actually rely on.
Well, it's they embedding in these theories mean that you can explain them starting from this sort of theory. So yes, I would say that.
Okay, I just wonder how this sits now with
the fact that we have not detected I mean, I think that there is still interest in exploring these theories, and I think that for all the time that we want to continue to look for supersymmetric particles, supersymmetry, sorry. I think it's interesting to continue to look at this sort of supergravity models as well.
Isn't it just that because inflation can happen at such high energies that you can have these theories anyway, even if we haven't found them today on Earth in labs or whatever?
Very good point.
Because they happen at such big energies, you could have these theories.
fair
They
enough.
could move the goalposts each time, right?
Well, that's kind
Like
of
if you
fair
can't
enough.
detect it, oh, it must be a higher energy.
Yes, thanks,
Well,
Raphael.
Okay.
Yes,
Yeah.
that's a very good point. So it's true. Accelerators work at energy scales that are
Okay, so they're not
widely
really
separated from inflation.
right. Okay, that answers the question.
Energy scale. Yeah, thanks, Raphael.
which is also why inflation is like a direct kind of test to these theories, I guess.
Ah, okay.
So cosmological alpha-attractors are born multi-field. Okay, so let's see how. They are naturally formulated in terms of a complex field that lives on the hyperbolic disk, sorry. And the field space curvature for the hyperbolic disk is constant, negative, and set by alpha. So that alpha is the thing that goes in the name alpha-attractors, okay? So you start with your complex field, you define some potential which will depend on it, and you can, at this point, expand your complex field in terms of two fields, a two-scalar field, a radial field, and an angular field. And so basically you are transforming your action from an action for zeta to an action for r and theta. Okay, so r is the radial field and theta is the angular field. So now, yes.
Sorry, I did not understand what's that pointer disk business, and what's that curly R that where the alpha appears.
So alpha sets the field space curvature of that disk. So this disk basically is you think it as the field space. So basically, space whose coordinates are the fields. Okay. So if you move around this space, for example, you can think about that you can use a vector to move around this. Now, the vector can be, the vector position can be specified in terms of the length of the vector and the angle. Okay, so this is where these are two fields actually living there. So what I think the take message from here is that the fields are living on a space. The fields are the coordinates on this space, and this space is not flat.
It has a curvature that's alpha or
that
related
is set by alpha.
Okay.
And this curvature is negative. Okay,
Okay.
this is another point that we will see playing a role later on.
When you talk about the space, do you mean the space time?
No,
No.
It's the space of the field.
yes. Is the space where
Okay.
these fields live.
Yeah, okay.
Okay, so as in the space time, you have coordinates that like an event is described by some coordinates. In field space, coordinates are your fields. So in this
Yeah.
space will be r and theta.
And how do
Okay.
you name the two? Like, how do you?
I think they are not really
Okay.
the same thing. They are different.
Mm.
But it's
Okay.
good to think about coordinates because
Yeah.
So you would have a field space metric. Is that
Yes,
correct?
yes.
Okay.
Yes. And from that field space metric, then you calculate, your
Curvature.
exactly. So the field space, basically, what is this telling us that there is not just the potential, so the multi-field potential that plays a role. There is also a hidden protagonist there, which is the field space metric. Okay. So now neither r nor theta are canonical. So next step is you transform to the canonical radial field phi, which is defined in terms of r in this way. Okay. And so the kinetic Lagrangian for phi and theta reads like this. Phi, you see, is a canonical field. Theta is non-canonical. And this is the g theta theta component of the metric. So g phi phi will be 1. G theta theta is that, and the mixed terms are just 0. And so basically you are there. So this is multi-field alpha-attractor. These are two fields living on a hyperbolic field space, and they will have some potential v of phi of theta, comma theta.
Can I just ask, the limiting case when alpha goes to infinity, is that a flat field space?
If alpha goes to infinity from our field space, yes, it's
Yeah.
flat.
I mean, so what happens to that thing? Is it-
It's just flat. So
Yeah,
it
it's
means
not
that there
constant,
will not be any term in front of the theta squared.
Right, so it's going to one, okay.
Okay, so now you have your multi-field alpha-attractor model, and that's why cosmological alpha-attractor are born multi-field. Now, two things can happen. Either theta is, let's say the theta is not stabilized. So it means that theta is dynamical, which means that during observable inflation, theta is doing something. Theta is not just sitting in a point and that's it. It's moving around. So better to say, the field space trajectory has some theta direction, let's say. Okay, in this case, you need to take into account the full multifield dynamics, and this has been done starting from this initial work. And another possibility is that actually theta is stabilized, so theta is non-dynamical, it just sits there. So you just move basically in the radial direction during observable inflation. And in this case, you can use an effectively single field description, which will be given only in terms of the inflaton field phi. So the radial field will play the role of the inflaton. And because of the canonical transformation that we have done before, the potential of the inflaton phi will be a function of hyperbolic tangent of phi. Okay, so that's why you think, maybe you already know a bit of alpha-attractors. That's why, for example, we look at potentials like hyperbolic tangent of phi squared or stuff like that. It comes from here. It comes from that canonical transformation. So, and then there is another important consequence of this canonical transformation that you have performed. So let's say that you started from a potential of, as a function of the original radial field R, which is ugly, and you cannot inflate on this because this is very steep. Okay, you need a almost flat potential to do the job. But then you transform to your canonical field phi, and when you go and look at how the potential looks like for phi, it will get transformed from here to there. And in particular, you see that there are regions now where the potential is nice and flat. And in some way, you have lost, and you can inflate here. oh, sorry, this doesn't work anymore, but you can inflate on that bit of the potential where it is well behaved and almost flat. And you can also see that we kind of lost memory of what the potential looked like before the canonical transformation. And this is at the core of these universal predictions. So when you go and calculate for alpha-attractor models, what are the first order slow-roll predictions for the tilt and the tensor to scalar ratio, you find that they look very simple. They depend on delta SMB and on alpha. And this is telling you that they don't depend, for example, on details of the potential, because exactly you lost memory of that potential because of the canonical transformation. So
Does it mean I mean, you can't really change the physics because you change the variable. It's just, it's not obvious. You have
this is
to-
the effect of the kinetic term. Okay, so yeah, you don't see it from this plot, but trust me that you can look at alpha-attractor from another point of view, and you can, if I was to write down all the equation, you could see there is actually a pole in the kinetic term. And it is that thing that then leads to this.
Right.
Yes.
Thanks.
So when you write the kinetic Lagrangian for that zeta and zeta bar fields, there is a pole at the boundary of the Poincare disk, and that is what then gives you alpha-attractors. Oops. Okay. So what we want to try to answer in our work is, okay, let's see that, let's consider these alpha-attractors that are very important and compelling models. We want to test them on small scales. So let's consider a possibility that they deliver some large scalar fluctuations on small scales. And since the cosmological alpha-attractors actually are born multifields, so we don't want to do this only in single field, but also in a multifield setup. And we want to try to answer these questions. So what small scale phenomenology can we have for models that are consistent with the CMB measurements? And whether there are similarities or differences between the single field and the multi-field approaches. So in the single field case, how do we do this? We consider a model and an inflaton potential that has an inflection point. So this is how the inflaton potential looks like. You see that it is a function of the hyperbolic tangent of phi for the reason that we have seen before. This is given by a cubic, basically a polynomial, a cubic polynomial, and it is endowed with an inflection point and depends on alpha, which, if you remember, is connected with the curvature of the hyperbolic field space, depends on the inflection point position and the first derivative of the potential at the inflection point. So if we plot this function for some parameters, this is how the potential looks like, and we have some regions where the potential is obviously here. I'm cutting the plot, but this is flat. So you can inflate, and then during your evolution, your inflaton will roll towards smaller values until it makes this gray point, which is an inflection point, and then inflation ends afterwards. So what happens is that at the inflection point, the slow roll approximation is violated, and you enter another regime, which is called ultra slow roll. So when you have extremely flat potentials, which is the case for an inflection point, if you think about it, how it is defined, the slow roll approximation is violated, and something strange happens. So let's look at the first two slow roll parameters against delta n. So basically, this is the end of the inflation, and this is the beginning of observable inflation. So for a specific potential, whose parameters are just defined there. I can't believe I need to resort to this, but it's true. So these are the parameters for this potential. And we start in slow roll, epsilon and eta are small, and then at a certain point something happens and eta gets large, while epsilon becomes just decreases. And eta gets around 3, let's say, eta its value is around 3. And then this happens around the inflection point, and then when the input on escapes the inflection point, it just rolls towards the minimum and inflation ends. And you see inflation ends when epsilon h reaches 1. So in terms of the perturbation, what does it imply having an ultra-slow roll phase? So I like to look at it like that. If we consider the curvature perturbation on super-horizon scales. So if we remember the scheme of scales that we looked at before, in single field, slow roll, zeta dot on super-horizon is 0. But we can look at an explicit expression for zeta on super-horizon scales, and there will be a constant mode, and then this second contribution. And this second mode depends on the values of epsilon h and eta h. In slow roll inflation, the second term is just exponentially suppressed, and so zeta is basically a constant, so zeta dot is 0 on super horizon scales. Good recovery result that we were expecting. But during ultra slow roll, what happens is that epsilon h is small, but eta h is not small. It's actually around 3. And so the second term is not suppressed, it actually grows. And so zeta will be given by a constant plus something growing, and is no more constant on super horizon scales. So basically, we expect perturbations to grow from ultra slow roll dynamics. And this is exactly what we find when we go and look at the numerical results for the scalar power spectrum produced by this sort of model.
Does this mean that there is some sort of superluminality involved?
No.
No.
Why? Why there should be?
Because on super horizon scales, I was expecting nothing to happen.
Oh, but that's in slow roll.
Yeah, I was just trying
Yeah,
to
yeah,
understand if in this extended field
Yeah.
it's true.
So you said that the curvature perturbation becomes non-constant on super horizon scales, but maybe I missed something. I was confused by how that. Why does that then imply that we get some? Why does that affect, say, perturbations that very, very small scales much below that, right?
Because these scale cross the horizon during slow roll.
Oh, so this is the
And
scale.
these scales cross the horizon around ultra slow roll.
Oh, because there's smaller scales now, so they're at the end of inflation.
So when let's consider.
So does ultra slow roll meet usually happen at the end towards the end?
Let's say that in this model we are putting it happening towards the end of inflation.
Okay.
Yes. So your zeta will be given by that constant plus another term, no? And that term is triggered anyways.
Okay.
When the ultra slow roll phase happens. But if theta that term was so small because before it was suppressed, even if you have a little growth, which is due to the ultra slow roll, you don't notice effects for these sort of scales.
Oh, so it's still
That
dominated by
cross-
the constant one or something.
Yes,
Okay.
the crossed very far from the ultra slow roll phase
Oh, so you only see it on the things that cross later.
around the ultra slow roll phase.
Okay,
Yes.
got it. Right. I forgot about that connection between like ultra slow roll and the happening towards the end of inflation.
Yes.
Okay, makes sense. Thanks.
I'm interested in what determines the value of K at the peak. I mean, how many parameters, there's alpha, but how many other parameters are there in the model?
I think we're getting here. So if you just hold this question,
Sure.
maybe I'll answer it. I'll answer to it. So this is what happens in the single field case, and we want to look at the large scale predictions for these models, and we calculate them numerically, and then we find that these results are well described by modified universal predictions. So if before, I told you that these are the universal prediction for alpha-attractor models, what happens now is that there is a new scale, okay? And this scale is the scale of the peak. So if we go back to this scheme of scales, it turns out that the large scale observables are no more set by this quantity, but this quantity. And so we can basically describe the large scale predictions in this way. I can change the position of the peak scale by changing the position of the inflection point. And this in turn will fix the prediction on large scales because of this. Does it make sense?
Yeah.
Okay, cool. So the peak, the K peak is selected by the position of the inflection point. The amount of enhancement is set by that psi parameter, which is telling you like how exactly is this inflection point.
So, but is it essentially arbitrary, or are there some constraints on the range?
So I don't think it's arbitrary. I think there are constraints, and the constraints are a consequence of this. And in particular, this is the consequence. So if we want these things these models that we are looked at to be compatible with the CMB, for example, we want that our NS predicted from these models are in accord with the measurement of NS, then this places a bound on the peak scale. So to be in accordance with the CMB, the K peak has to be located at very small scales, like larger than 10 to the 18 inverse megaparsec, so very, very small. And this has very big and important consequences for the small scale phenomenology, okay? Because you have bounded the position, at least you say, you have bounded the position of the peak not to be on certain scales. So for primary black hole production, you can have basically, you have two scales, the CMB scale and that here I also put the reheating scale, which is the scale that re-enters the horizon at completion of reheating. And the bound that I've shown you before is just telling me that I cannot pick peak scales that are above this red line. They have to be below, okay, if I don't want to spoil the CMB. So for example, I can pick to the two scales, the blue one, the K peak, blue crossed before the horizon before K reheating. The second one, the purple one, crossed after K reheating. And you see that these will behave differently because they cross the horizon in different phases. The purple one crosses the horizon during reheating, which is a matter-dominated phase. And the blue one crosses the horizon during radiation domination. So we basically need to consider two different primordial black hole production scenarios. For the blue scale, we need to consider PVH formation during radiation domination. For the purple one, formation during reheating. We have done this, and we have considered all the possibilities, and we have found that if you want to stick with this, which puts your model not in tension with the CMB, then you will produce primordial black holes that are actually extremely light. These primordial black holes are so light that they would have evaporated by today, so they are not a candidate for dark matter. Okay, so for these models, CMB measurements really constrains your small scale phenomenology. Yes.
How quickly would they have, say that they were the upper end of that bound, so 10 to the 8 grams?
Yes.
How quickly would they have evaporated down?
Honestly, I don't know, but I know that they are gone before Big Bang nucleosynthesis.
Okay, right. So really, really early.
Yeah.
I think 10 to the 14 grams would black holes formed during that time with a mass of 10 to the 14 grams would be evaporated by today.
Okay.
So 10 to the 8 would be evaporated.
Okay, so redshift.
I don't speak
Maybe,
redshift.
yeah, I've got no idea. I'm just.
But it's fine. We can look at that
Okay.
easily. It's
So
just-
very early is the
Yes, yes.
is the short answer.
Yes.
That's thanks.
When you say it's not a candidate dark matter, means it doesn't represent the whole of dark matter, or it can't be a tiny fraction.
Cannot be. No, if you want something to explain dark matter, it needs to be around now, today.
Yeah. Oh, okay.
These are gone.
Okay, I see.
These are long gone. So it's not even a matter of
Yeah.
do these primary black holes have the right masses to account for the totality of dark matter, or they can just account for a bit of it.
They don't
They're
exist
just
anymore, so they can't.
they're not there. So
It's about a tenth of a second. What's your-
Okay, right.
it's about
A tenth of a
Thank
second.
thank
a
you.
tenth of a second. Thank you.
When was the Big Bang nucleus in
Oh, about 100 seconds.
Okay, right.
A tenth of a second, okay, yeah, they're gone.
Yeah.
So I will leave the secondary gravitational waves for just the last slide. So just hold for that. Let's jump to the multi-field alpha-attractors. So this is basically saying, you know, I want to enhance the scalar fluctuations, but now we want to consider the two-field full alpha-attractor model. And we decided to consider a variation of the model that I've shown you before, but now this is a multi-field model. So we put an inflection point at position pi inflection in the direction of θ equals 0. And this is how the multi-field potential looks like. So it really looks like the one that you've seen before. It still depends on the hyperbolic tangent. Still there is linear quadratic cubic term. Still there are these two parameters that were there before. Now psi is not there because psi is 0, because this is a stationary inflection point, but that's not relevant. So I don't want you to focus on filters. There is just this term that showed up, and you see that this depends on theta. So here we have our multi-field model. If we plot it, angular direction, radial direction, this is how the potential looks like. There's nothing really too much crazy about it. And if we look at how the fields move on this potential, we can plot some trajectories corresponding to different starting initial values for the angular field. So this is the angular field again, this is the radial field. This is the beginning of observable inflation. Let's just focus on one of these lines. Let's pick this one. So you start rolling just in the radial direction, and then at a certain point of your evolution, you start rolling also in the angular direction. So there is a turn in field space. Then there is some complicated dynamics happening, and then here inflation ends. So what we see from these models is that inflation is realized in two phases. First, you roll in the phi direction, then you roll a bit in the theta direction. And the transition between these two phases will have a large turn in field space, just because you literally do this and that. And when you turn in field space, you can describe this with a dimensionless parameter, which is called eta perp. So we expect eta perp to become large. No, we see that eta perps become large at the turn. Now we are in a multi-field, to be precise, two-field inflation model. So we need to a bit review, the perturbations. So since this is a two-field model, there will be two types of perturbations, scalar perturbation, and we call that zeta, the curvature perturbation, and then this has a curvature perturbation, QS. On superhorized, in order to understand the dynamics of this fluctuation, I think it's useful to look at the superhorizon regime. What happens is that zeta dot is not 0, but will depend on the second perturbation, on the isocurvature perturbation. So in presence of a turning trajectory, so eta perp is different from 0, you can have sourcing from the isocurvature perturbation to the curvature perturbation. Now, the isocurvature perturbation has its own equation of motion, and in particular, its effective mass is given by 3 terms. Some Hessian of the potential, which we expect is just the say, non-flat version. And then a term that depends on the field space curvature, and a term that depend on the bending parameter. Now, let's entertain the possibility that we are working with a model where the field space curvature is negative, and this is the case for alpha-attractors. And let's, again, consider the possibility that the second term, this one, is much larger than the other two, so it dominates here. Now, since the field space curvature is negative, we will have an effective mass, square mass that is negative for QS. So what happens to QS is that it will just grow tachyonically. And because of this, it will source scalar perturbation. So this is just a scheme of trying to understand what's going on with the perturbation in multifield. And indeed, as I already a bit spoiled for you, we see that in these models, the ice curvature perturbation experiences a tachyonic instability. So if we go and plot the effective mass squared, which is the white line, we see that at a certain point it turns negative and large. And who is causing this? Exactly this term. Okay, you see the purple term is the term that contains the field space curvature, is larger negative, and it drives the effective square mass to be negative. So we remember that the field space curvature is set by alpha. So let's see the effect of changing alpha from 0.1 to 0.005. This corresponds to changing your field space curvature from -13 to -266. So basically, you are going to larger and larger in magnitude values for the field space curvature. What happens is that if you go and look at the scalar power spectrum produced by these models against scale, you see that they exhibit a peak, and the peak is higher and higher depending on the value of alpha. And this is explained if we remember what was going on. So the larger the field space curvature in magnitude, the more unstable will be this field, which in turn sources the curvature perturbation. So this is where this peak comes from multi-field effects, not from the inflection point. And the peak enhancement is set by alpha and the initial value of the angular field. So now if we go and look at the large scale predictions, what happens is that we find exactly the same thing that is going on in the single field case. So we can vary the position of the peak, changing a parameter of the potential, but this will change slightly the scalar power spectrum on large scales. So this will change the tilt of the scalar power spectrum on large scales. And as we found for the single field, the modified universal predictions describe these results, and this limits the phenomenology on the small scales exactly as in the single field case. So we are at the end. Let's just, I said a lot of words, so let's just recap the key points. So we have looked at two different models, single and multi-field within alpha-attractors that produce large scalar fluctuation on small scales. So this line corresponds to a single field model, and this line corresponds to a multi-field model. Take-home message, they come from different effects, okay? Different things are playing a role in the single field and in the multi-field case, but they will look like the same on large scales, okay? Because what happens on large scales is fixed solely by the position of the peak, not the nature of the peak. Let's finally look at second order gravitational waves. So they can be large because the scalar power spectrum is large, but because you want not to spoil the CMB, the peak scale will be located at scales larger than 10 to the 18. Therefore, also the second order gravitational waves peak will be at very, very small scales, which is beyond the reach of gravitational waves observatories. Now, there are differences between the signal that you would get from the single field or the multi-field model, and I'm happy to discuss about that, but I think in the interest of time, we are ready to finish. So we have studied exponential alpha-attractors and considered models that delivers large scalar fluctuation on small scales. In the single and in the multi-field case, they come from different effects. If you want not to spoil the CMB measurements, you find that the peak in the scalar power spectrum has to be located at scales that are larger than 10 to the 18 inverse megaparsec, so super small scales. So therefore, compatibility with the CMB constrains your phenomenology. The primordial black holes would have evaporated by today, and the second order gravitational waves peak at ultra high frequencies. Okay, I'll stop here. Thank you.
All right, thank you very much. Do we have any questions? Either online or in the room? Go ahead.
So in the last slide you showed, it means that if in the future